Chapter 3, multiple choice review time. Let's get it done. 1 and 2 refer to the same information here. It says for children between the ages of 18 months and 29 months, there's an approximately linear relationship between height and height and age. There we go. The relationship can be represented by y hat equals 64.93 plus 0.63x, where y is height in centimeters and x represents age in months. So number 1 says Joseph, little baby Joey, is 22.5 months old. What is his predicted height? Well, this is his actual age, which we would use in x. So if we were to plug into our calculator 64.93 plus 0.63 times 22.5, we should get as an answer, rounded here, to be 79.11. I believe I got 79.105, which rounds to be the 79.11. For number 2, Loretta is 20 months old and is 80 centimeters tall. What is her residual? Now, residual, we have to remember, is error, and error is calculated as actual minus predicted. Well, they gave us how tall she actually is 80 centimeters. Now, how tall do we think she's going to be at 20 months? Well, we'd have to do the same thing like we did with baby Joey. We'd have to plug in 20 into x, and so 64.93 plus 0.63 times 20 would give us 77.53. So subtracting actual and predicted would leave us with a residual of 2.47, positive 2.47. Now, keep in mind, we could end up with a negative residual if our actual, in this case, if our actual height was smaller than what we predicted it to be, if we overestimated. So since we have a positive residual, we really underestimated because we thought Loretta was going to be shorter than she really was. Number 3, you have data for many families on the parents' income and years of education their eldest child completes. Your initial examination of the data indicates that children from wealthier families tend to go to school longer. When you make a scatter plot, they want us to figure out what's the explanatory variable and what type of association would we see. Now, association is basically, do we see, as x increases, y increases, as x increases, does y decrease, or is there really no association? Which means that the correlation would be close to 0, which means our scatter plot would be fairly scattered and circular in nature. So they were using income, wealth, to try to predict how long they would go to school. So parents' income, check, 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 A, B, and C works out here, but D and E don't use the correct explanatory variable. Now, would we see a positive, a negative, or really no association? Well, it says our initial examination of the data indicates that wealthier families tend to go to school longer. So there is an association that we see from the data, so it's not C, but now is it positive or a negative association? So we need to think of as income as our explanatory and education, years of education, as our Y, and it says that wealthier families tend to go to school longer. Well, wealthier families would be down here, more years of school would be up here, which means we're going to have values that are in this vicinity. Wealthier families tend to go to school longer, which means that if they're not as wealthy, they're not going to go to school as long. So we should have some sort of scatter plot that looks like this. And it has a positive association to it. It has a positive slope if we were to look at the least squares regression line. So our answer to number 3 would be B. Number 4, a community college announces that the correlation between college entrance exam grades and scholastic achievement was found to be negative 1.08. On the basis of this, you would tell the college that entrance exam is a good predictor of success, the exam is a poor predictor of success, students who did best on the exam will be poor students, students at the school are underachieving, and the college should hire a new statistician. Now, if it's negative, that means we have a negative correlation. So the higher the exam grades, the lower the scholastic achievement. So, we would maybe kind of think maybe it kind of looks like this. But one thing we got to keep in mind here is if they're saying this is correlation and it's negative 1.08, you're going to have to think about correlation, we said, had to be strictly between negative 1 and positive 1. And this negative 1.08 is outside of that range. So as silly as answer choice E kind of seemed like initially at first, That is the answer. We need a new statistician that understands that correlation can't be anything less than -1. Number 5. An agricultural economist says that the correlation between corn prices and soybean prices is R equals 0.7. This means that. So first let's discuss, before we try to determine what the 0.7 means here. So if the correlation is 0.7, number 1, I know it's positive, which means if I were to consider a scatter plot, that means overall, in general, the points are increasing from left to right and up and down. So if they talk about, prices of, we'll say corn prices, maybe this is soybean prices, they didn't really specify, but with correlation, it doesn't matter which one's the explanatory and which one's the response. So typically it's going to look like here with a positive correlation, that as corn prices increase, well, soybean prices will increase as well. And if one decreases, then the other one will probably decrease as well. So when corn prices are above average, soybean prices also tend to be above average. This sounds pretty good. So let's kind of leave A. I'll kind of make a little mark there to indicate that's probably going to be our answer, but let's look at the others and see why they're not right. There's almost no relation between corn prices and soybean prices. Well, no relation means that R is going to be close to 0. And we have a 0.7, which isn't close to 0, so it absolutely can't be B. When corn prices are above average, soybean prices tend to be below average. Well, this is implying a negative correlation, a negative R, and we know we have positive, so it can't be C. D, when soybean prices go up by $1, corn prices go up by 70 cents. Well, they're trying to use the slope interpretation with the wrong value. You can't use the 0.7 to interpret it as kind of a slope. So that's off. And then E, the economist is confused because correlation makes no sense in the situation. Well, we can calculate correlation if our two variables are both quantitative, meaning that they are both numerical. And corn prices and soybean prices are numerical things that we can do quantitative things with, so it actually does kind of make sense. So it really must be the A we initially thought. Number 6. A regression of the amount of calories in a serving of breakfast cereal versus the amount of fat gave the following results. So here's basically our regression line. Which of the following is false? False, not true, false. So it is estimated that for every additional gram of fat in the cereal, the number of calories increases by about 10. Well, this sounds an awful lot like the interpretation for slope of a regression line. And so the slope of our regression line is the 9.625. Now, is that about 10? Yeah, it's about 10. I mean, if we were to round up 9.6525, it would be 10. And it says since it increases, is it also positive slope? And it is. So everything matches up there. So at first glance, you might go, hey, that's our answer. But that was a true statement, and we're looking for a false statement. So it is not A. Part B. It is estimated, erase that real quick. It is estimated that in cereals with no fat, the total amount of calories is about 97. Well, this sounds a lot like they're trying to do y-intercept interpretation. With no fat, basically we're saying when x is 0, then this would be our y-intercept value. Well, our y-intercept value was the 97.1053, and that's about 97, so that's a true statement. So it's not B. C, if a cereal has 2 grams of fat, it is estimated that the total number of calories is about 116. So we're using an actual value for fat, which we could plug in over here. So if I were to put in my calculator, 97.1053 plus 9.6525 times 2, what am I going to get? So let's see real quick. Calculator. I get 116.4103. So yeah, it's about 116. So that's a true statement. D, the correlation between amount of fat and calories is positive. Well, let's see, correlation, that's R. Do we know if R is positive? And we do know R is positive. How do we know if R is positive? Because it has a positive slope. So the scatter plot would have to look something like this so that the line of best fit has a positive slope to it. So that is true. So we get down to E. E's got to be our answer, but let's figure out why it's got to be false. So if one cereal has 140 calories and 5 grams of fat, its residual is about 5 calories. So we're talking about residuals again. So we need to know the actual minus the predicted number of calories. They gave us the actual. There's actually 140 calories in the cereal. We need to figure out, based on 5 grams of fat, what would be the predicted number of calories. So 97.1053 plus 9.6525 times 5 gives me 145.3678. And if I subtract those, I'm going to get negative 5.3678. And at first glance, you go, well, that's about 5, right? But this is implying a positive 5 residual, and we got a negative 5 residual. So it is close to being the truth, but the sign is off. So that is why E must be the correct answer. Number 7. A copy machine dealer has data on the number of copy machines X at each of 89 customer locations and the number of service calls in a month Y at each location. Summary calculations give the mean of X, the standard deviation of X, the mean of Y, the standard deviation of Y, and the correlation all to be those specific numbers. What is the slope of the least squares regression line of number of service calls on number of copiers? So let's see. The LSRL of service call on number of copies. Well, number of copies is X. So basically they're saying using X to get our regression line of Y. So we're saying Y hat equals something plus something X. So our number of copiers is our X here. And you might go, well, why does that really matter? Well, we need to know which one's X and which one's Y. Now, they didn't give us the data here, but they did give us summary statistics. And on your formula sheet, this is where they look like B0 and B1. So if you remember, Y hat equals A plus BX. A was our y-intercept, but on our formula sheet, they don't call it A, they call it B sub naught. And if you look at your formula sheet, it should say y bar, the mean of y, minus B1, which is the slope down here, times x bar. Now, they just want to know what's the slope, so we're going to be using this guy down here. So B was our slope, but in our formula sheet, that's B sub 1. And the formula for it, if you look at your formula sheet, is R times the ratio of the standard deviation of y to x. And we have these numbers. So the correlation was 0.86, standard deviation of y was 3.8, standard deviation of x, 2.1. So just plugging that into my calculator, and we don't need any kind of special parentheses because everything's multiplication and division, I get 1.556, which is closest to answer choice B. Now, if they'd asked for the y-intercept, then we'd have to take that number, plug it in up there, take our 8.4, plug it in there, take our 14.2, plug it in there, and then do the math, and then we could have the y-intercept. Number 8, in the setting of the previous problem with the copy machines, about what percent of the variation in the number of service calls is explained by the linear relation between number of service calls and number of machines? If you've been paying half attention, this sounds like the interpretation for something that we discussed late in the chapter. And hopefully, if you are awake and not a zombie, that was R squared for how we interpreted that. Now, we were told that R was 0.86. So to get R squared, we're going to square 0.86. So 0.86 squared gives me 0.7396, which is closest to answer choice C. Number 9, which of the following relationships is most likely to result in a strong negative correlation? Correlation, that's R. We need it to be negative, and we need it to be strong. So strong, maybe like we'll say 0.9 is strong. So, but we're going to have negative 0.9, which means if we were looking at a scatter plot, we would need to see something that's going downhill and our points are almost making a straight line. So we need to consider which one of these scenarios where we have our x and our y, where an increase in x would result in a decrease in y. Okay, so we're kind of looking for a relationship that works inversely to each other and not directly proportional. So let's start with A. The number of people showering in a college dorm and the water pressure in each shower. Well, some of you might not necessarily know the relationship between number of showers going and the water pressure. Water pressure is how strong the water comes out of your shower head. And if there are many people using the shower water pressure is going to decrease because more people are using water and you have to exert, much more water into more places, so the pressure will have to decrease. So as the number of people showering increase, that means our water pressure is going to decrease. So this is looking like it's probably the answer. But let's make sure that you understand that the others maybe show a positive relationship. So the outdoor temperature and the number of fans running in non-air conditioned dorms. Well, as outdoor temperature increases, would we expect the number of fans running in non-air conditioned rooms to decrease? Because that would show a negative correlation. And no, we would expect that number to go up. So we expect B to really be a positive correlation, probably a strong positive correlation. C, the comfort rating of a mattress and the number of hours of uninterrupted sleep obtained. So if we increased the comfort rating on a mattress, we would think, hey, if the comfort rating goes up, we're pretty comfortable, we're probably going to sleep for more hours and not less hours, right? So again, we would expect maybe positive correlation here. D, the price of a home and its square footage. So as the price of a home gets more expensive, would we expect the house to shrink more? No, we would expect it to become bigger. The more we're going to pay, the bigger the house needs to be. So it's not D. Now E, fuel efficiency of a car in miles per gallon and its speed. Now we did an example in the book that was related to this. And at first you might think, all right, as speed increases, your miles to the gallon's going to decrease, right? Because the faster a car moves, the more energy it needs to consume and its fuel efficiency is going to drop. Okay, but we also talked about what if you're traveling 0 miles an hour, your fuel efficiency is going to be 0. So we talked about, if you remember this, the graph kind of looked like this. That eventually, that somewhere, there's kind of this sweet spot around, and this is why initially speed limits were 55 miles an hour, because math was done to figure out, hey, at 55 miles an hour, that's about the sweet spot for where cars reach maximum fuel efficiency. If you didn't know that, that's why. But before that, it's not that great. The slower you travel below 55, the worse the fuel efficiency gets. But if you go over 55, then it starts to decrease. So do we have a negative correlation here? Well, number one, we don't really have a correlation, right? Because correlation's for linear relationships, and this is not linear. Plus, it's positive here, and then it's negative here. So we kind of get, two things that are contradicting each other. So E seems like if you only consider this part of the graph, then yeah, it's strong negative, but the first part of the graph is not. So the answer really is A here. And the last one. Mr. Nerdley asked the students in his AP Stats class to report their overall grade point averages with their SAT math scores. The scatterplot below provides information about his students' data. The dark line is the LSRL for the data, and its equation is that. Which of the following statements about the circled point is false? If you don't have eyes, that's the circled point, which I kind of made like an eyeball. Isn't that kind of cool? Be like, ugh, mean. Get like mean, grumpy eyebrows in there. We can get like some bloodshot eyes going on. Like, oh man, this dude is like totally ticked at you. Anywho, let's see. Which one is false? This student has a grade point average of about 2.9 and an SAT math score of about 690. So let's see. If I were to drop straight down, it hits the GPA line at a little bit less than 3. So yeah, it's feasible that it's about 2.9. And if I were to shoot straight over, where does it hit the SAT math score? Less than 700, so about 690. Yeah, that seems feasible. So this seems like it's a true statement, and we're again looking for false statements. So A doesn't look good. If we used the least squared regression line to predict this student's SAT math score, we would make a prediction that is too low. Well, where was the student's actual SAT math score? Well, it was, different color here, it was about that 690 mark, right? So we could use the 2.9 GPA and we could plug it into X and get what the prediction is and compare that to 690, but we don't really have to do that because the LSRL is our predicting line. So where does a 2.9 GPA, get a different line here, if I were to go straight down to about 2.9, where does that hit the LSRL? Well, it hits it around right here. So where does that hit the y-axis over here? Well, it hits it around a little bit above 600. This would be our prediction. Okay, if I were to plug 2.9 into here, I should get something that should be something a little bit greater than 600. I'm not actually going to do the math. I'm going to use the graph to make that prediction. So this is what we would predict, something greater than 600. And it says we would make a prediction that's too low. And that's true. This was our prediction, a little bit greater than 600. He really scored a 690. So yeah, we underestimated. Where are we at here? C, the student's residual is negative. Well, again, we said this was the actual. This is the predicted. So if I did actual minus predicted, would I end up with a negative number? No, I'd end up with a positive number because I got a big number minus a smaller number. So this should be positive. But it says negative, and hey, that's our false statement. So let's look at the other two just to make sure, see why they are true. Removing this data point would cause the correlation coefficient to increase. So let me get rid of all these here. If we were to knock out this point, would that cause R to increase or decrease? Well, what we need to consider is, well, how far off is it compared to all the other points? Well, if I were to drop vertical lines to the LSRL from each of these points, some of them are positive, some of them are negative, depending on where the points are located. If I were to look at, and I'll make our circle points residual a different color. So again, I'm making all these residuals here. Really, that guy there has a super teeny tiny residual. So let's make the other one orange. So if I were to compare this residual with all the others, how does it compare to all the others? Well, it's a big residual, right? It's one of the biggest ones. Is it the biggest? I don't know. This one here looks like it might be bigger than that one. So, but still, on average, this residual is bigger than most of these others. So if I were to get rid of that point, aka get rid of its residual, how would that affect the overall correlation of the rest of the points? Well, that would make all the rest of the points closer to each other. And so it would cause it to increase. So that would be a true statement. And then E, let's make sure this is true. Removing the student's data point would increase the slope of the regression line. So again, if I got rid of this, if I got rid of this point, that's going to affect the location of the LSRL. Now, if I were to try just to estimate where I think the LSRL would go, you know, if I just try to eyeball, where does it look like the line would hit roughly about half above, half below? I don't know. What do you think? Probably, I'd say somewhere about in this vicinity. And that slope looks pretty good. This slope that I drew in has a positive, it's a bigger slope, so it would increase there. So it is also true. Now, hopefully, running through those problems there will help you kind of identify strengths and weaknesses that maybe you need to cover before we get to the test. And that is all.